teacher of chemistry at the University of Leuven in Belgium, and today and for the rest of this and next week I will be teaching the General Chemistry 2 course to you. So looking forward to our interactions, and I'm actually a teacher of General Chemistry 1 and 2 in Leuven, so I'm using the same course as I have there. So this is why we start with chapter 10 and not chapter 1. So, and the first chapter is about stoichiometry, and there will also be a part of solutions that will match with the things that you need to study at your university. So let me first explain to you what we understand by stoichiometry. It's in fact a quantitative approach. It means we calculate things. We want to know the value of numeric value of things of a certain reaction. Normally you may have reaction A to B, and then you want to know what forms, maybe it is C or maybe D. That is the qualitative approach. You know what is going on. Quantitative approach needs, we want to know how much is being formed of the compounds number C and number D. And this we can find out by calculations that are based on the reaction equations. So I think you have already learned how to make a balanced reaction equation. So we're going to need that to make our stoichiometric calculations. Then this also has a practical value. For instance, if we do titrations, we will need to do stoichiometric calculations after we have done this practical work. So, what do we need for stoichiometric calculations? We need the reaction equation, we need the coefficients, so how much mole of each amount is reacting in the reaction equation. And from there we can do tutorials, exercises, and that are based on this stoichiometry. I will give a few examples. For people who don't know what is a titration, so this is it. Typically, you add certain reagents with a so-called burette, and the burette has like gradings onto it, so you can see how many milliliter of a certain solution you have added. And typically, there's an indicator that tells you when the reaction is finished. For instance, by a color change. So this is typical acid-base titration, in which we know that it's the end by the change of the color from white to this pinkish color. So let's take a very simple reaction. The burning of dihydrogen with oxygen to form water. So you can see the first thing we need to do is the reaction equation. And you can see to prepare 2 moles of water, we need 2 moles of dihydrogen and 1 mole of dioxygen. Now, the mixture of gases that we start from is in fact equimolar, meaning we have the same amount of moles from each. And then we see what is happening. Now, the first thing that you see is that the reaction would require a 2-to-1 ratio of the reactants in order to be able to react. That means 1 reagent is in excess, because for the 0.1 moles of the hydrogen to react, we need only the half of it. So 50 millimoles And then after that, all of the hydrogen has disappeared. So the reaction stops. That means 50 millimole of the original dioxygen has reacted. 50 mole is staying. So after the reaction, there is still dioxygen. The dioxygen, in other words, was in excess. Afterwards, we get 100 millimole, 0.1 mole of the water. So in the mixture there will be water and there will be dioxygen. So this is a very common situation where the amount of reactants is, relatively speaking, not the same as the amount that we would need in the reaction equation. And then we can say that reagents that is left behind after the reaction, that's the reagent that is in excess. The other reagent is what is limiting the reaction. The reagent that is not in excess is the limiting reagent. So in this case is the dihydrogen. Why limiting? Well, it can only go until this reagent is used up. And that's the maximum that you can reach. So this is the limiting our reaction. Now, what we previously had was not a stoichiometric mixture. What would be a stoichiometric mixture is one where we had 0.2 millimole of dihydrogen and 0.1 millimole of dioxygen. Then you have the exact ratio. That is also the ratio of the coefficients in the reaction equation. In such a situation, all of the reagents will have reacted after the reaction. There's no more reagents left. None of them was in excess, none of them was limited. It was a stoichiometric mixture. But in all of the other cases, there always will be a reagent in excess and a reagent that is limiting. Okay, so far I have done as if all reactions always give 100%. So they always go completely. But in the real world, it is not like that. There are maybe side reactions or incomplete reactions due to equilibria or something like that. So we don't have 100%, we have a number that is smaller than that. And people say there's a certain yield. 100% yield is said to be quantitative. That's the theoretical peak, what you would expect. But in the practice there will be a lower yield, maybe 90%, maybe 80%, or depending on the case. In organic chemistry, for instance, yields are very important. So high yield is considered to be 90 plus. The low yields is maybe 20 or 30%. So if we have a homogeneous mixture, so a solution, for instance, that means all of the parts of the solution have the same composition. In that case, we can, instead of working with moles, work with mole per liter, with concentrations. And I think the most convenient is that we use the molarity, so how much mole is in a liter, and then this can be used for the calculation. Now, it may be that you add two reagents in their own solvents, and in other words you mix, or it may be that you add solvents, in other words you dilute. In such case, the amount of mole is not changing, but the mole per liter is going to change. So you have to take that into account, and I'll come back to that later. So after you have done this accounting for, then you can start, initiate your calculation. based on the stoichiometric coefficients. So let me now give you a very simple example. So it's a reaction of iron 3 with tin 2. It's in fact an oxidation reaction, and we'll have a chapter later on equilibrium of oxidation reactions. But here we can assume that the equilibrium is completely to the right. In other words, it's a reaction that goes as far as it can go. So we are given the concentrations and the amount of reagents. So we have 20 milliliter of a 0.4 molar solution of iron 3 to start. We dilute it to 100 milliliters. So that means the amount of mole stays the same, but we will have a dilution factor of 5, 20 to 100. We take 10 milliliter of this diluted solution and we mix it with the same volume, 10 milliliter, of a solution that contains 0.60 millimole. So here we give the concentration of tin 2 ions. Now, if you add 10 milliliter to 10 milliliter, of course, obviously you have 20 milliliter. We have to take into account this dilution again. So now it is asked, after again dilution is 20 milliliter to 50, what is the concentration of all the ions in the mixture? So in the first step, we're going to calculate before the reaction. Then we're going to see what is the limiting reagents. We're going to do the reaction and then calculate again what will be the concentrations then. So step by step. So we start with 0.08, so 80 millimole solution. We dilute to 1/5 of the original concentration. We take 10 milliliter out, mix it with 10 milliliter. So now we have half of the molarity because we dilute it with an equal volume. The tin also has to be divided by 2 because 10 milliliter became 20 milliliter. So that means these are the concentrations at the beginning of the reaction, 40 millimolar and 30 millimolar. Now, if you look at the equation, we need 2 irons for 1 tin. Afterwards, we form 2 irons, 2 plus, and a tin 4 plus. Now, even though there is more iron 3 plus, this is the limiting reagent. Because if we react completely, we have to react only 20 millimolar of the tin. And there will be tin 2 plus left behind. How much? Well, 10 millimolar. The iron 3 plus has completely gone because it was the limiting reagent. Now the iron 2 plus that is formed, we can see there's 2 times as much as the tin 2 plus that has disappeared. So that's 40 millimolar. At the end, we will have 40 millimolar of the iron 2 plus. What about the tin 4 plus? For every tin 2 plus, there is a tin 4 plus being formed. We are going to react 20 millimolar of tin 2 plus, so we form 20 millimolar of tin 4 plus. So these are the concentrations after the reaction due to a stoichiometric calculation. Not so difficult, but just you have to keep into account all the effects of dilutions. So iron 3 plus, in fact, the concentration is close to 0, but not exactly 0. It will be a very low number. We will see in one of the next chapters how we can calculate that number. But for now, we just assume it to be 0 or close to 0. To exactly calculate it, we need equilibrium constant. And we will teach you in a few chapters what does it mean and how can we do the calculation. So, you see the reagent in excess, tin2 plus, is staying behind after the reaction. This is typical for the reagents in excess. By the way, this is not the end, because we actually diluted the 20 milliliter to 50 milliliter, so we should not forget also to take that into account. That means these concentrations were the concentrations at 20 milliliter, so at 50 milliliter, the concentration becomes 2/5. So we have to multiply by 0.4. That means now this becomes 4 millimolar, 60 millimolar, and 8 millimolar after the reaction. As we can derive from this stoichiometric calculation. Okay, so we want to go to a part of stoichiometric calculations that has to do with working with gases. And before we can do our calculation, we have to use some theory, namely gas laws. So, and this we have to use for whenever we use reactions that are occurring in the gas phase. Because until now it was mainly into solution that we have talked about, like this tin2 plus and iron 3 plus. So, what does the ideal gas law say? It's P multiplied by V, and P is the pressure, V is the volume of the gas, that equals nRT. Now, N is the amount of mole of gas. So, it's in fact refers to the amount of particles that we have in the gas. R is a constant, the so-called gas constant. Now it depends on the unit of pressure, what is the value of R. If we use atmosphere, that is most common for pressure, then it's 0.082. Then T is the temperature, but be careful because it's a temperature in Kelvin, so-called absolute temperature. So if you normally you will get a temperature in Celsius, so then you have to do a recalculation from the Celsius to Kelvin. If the pressure is given not in atmosphere, but in Pascal or in kilopascal, the amount is 8.3 for R. This is typical for thermodynamic calculation. And then we will see that next chapter. But if we do PV nRT calculations, then it's based on atmosphere, or R becomes different. So this is a very common mistake. If we do exercises, that we take the wrong R in the calculation. So take care of that if you are doing it. So atmosphere, this is the value that you will have to take. So ideal gas, what does it mean? In an ideal gas, it is theoretically assumed that particles of gas are in volume and they are just moving around chaotically and they are not interacting with each other. They just take place. And this gas law is based on that assumption and on the statistical analysis. Now, in the real world, again, gas may be, the particles may be having some small interactions, with each other, so they're non-ideal. But we can still use this PV-nRT equation without making too much mistake. So that means we assume ideal behavior even though it is not 100% correct in our calculations. Now, just a few consequences of this PV-nRT law. So if we know all of the parameters, of course, that is not a problem, but if we have 3 of the 4 and 1 is unknown, then we can of course easily calculate the number 4, because R is a constant. So all of the other we know, so we can calculate P, V, N, or T, whatever is relevant. So here we have a very simple example. So this is a reaction where some gas is involved. We start with potassium chlorate, so that's KClO3. And we are forming KCl, so that means all of the oxygen is lost. And that means you will form a gas coming out of your reaction. And so suppose the potassium chlorate is heated. What stays behind is potassium chloride. So the gas is escaping. And actually you make the gas go out. And here it is taking a volume in this reverse cylinder. And we can actually measure that volume. It's supposed to be 1.44 liter at 20 degrees Celsius. The ambient pressure around is 1 atmosphere. That's what we are having also here in this room. About 1 atmosphere. So now, based on these data, we should do a calculation. And so it's asked to calculate how much mole of potassium chlorate has been decomposed to form this amount of dioxygen. So the first thing we have to do always is make the right equation with the right coefficients. Because that is the start of our calculation. So this is it. You see the relation between the potassium chlorate and the oxygen. We need 2 mole of potassium chlorate to form 3 mole of dioxygen. Now, the amount of mole of dioxygen we can easily calculate. So this is, we have PV-nRT, and what we need is N, the amount of mole. So N is PV divided by RT. Do we have P? Yes. Pressure is 1 atmosphere. Do we have the volume? Yes, it was given. 1.44 liter. R is an atmosphere calculation, so 0.082. And the temperature was 20 degrees Celsius, and that's 293 Kelvin. So it's 273 plus the amount of Celsius. So if you do all of that, you can calculate that there's 0.060 mole, so 60 millimole of dioxygen being formed. Now, that's okay, but actually we asked not about dioxygen, but we asked about potassium chlorate. How much is being formed? Well, to know that, we have to look at the equation. And you see, for 3 moles of dioxygen, you need 2 moles of potassium chlorate. So that means if you have 60 millimoles need 40 millimoles of potassium chloride. The same ratio of 2 to 3 we apply to the 60 millimoles. And then we arrive at 40 millimoles. So you have to multiply by a factor of 2/3 to come from 60 to 40. And 2/3, that's exactly the ratio that we have in this equation. Now, suppose we know only 2 parameters that are changing of the 4. Then, of course, it's not possible to calculate because we are missing data. But what we can know is that one parameter that we don't know is changing. The other one has to change along with it, because there's going to be a linear relationship. And for instance, we can calculate the molar volume of any gas at a temperature of 273 Kelvin, so that's 0 degrees Celsius, at a pressure of 1 atmosphere. So this volume is nRT over P. Now, suppose we have 1 mole. The R is again 0.082 because it's an atmosphere pressure, and 273 was the temperature in Kelvin. So you can see this then shows that we have 22.4 liter for a mole of gas. Any gas. Doesn't matter what is the chemical composition of this gas. It's always going to occupy the same volume according to the ideal gas law. So this, in fact, you can say that the volume of a gas is also a colligative property, meaning it's only dependent on the amount of particles and not on the type of molecule that we are investigating. And I will show later in this talk some more colligative properties in solution. So that means the volume of the gas is always the same if you have the same amount of mole. But the density, of course, will be different. Because in the same volume, we might have very heavy particles or very light particles. So, for instance, dichlorine has a molecular mass of 71 grams per mole. So, at a pressure of 0.95 atmosphere and 25 degrees, we could calculate what is the density of this gas. So, again, we can use PV and RT. And we'll see that we have 39 millimole of dichlorine at this temperature for 1 liter. In fact, this amount of mole will be for any gas, not only for dichlorine. Then the mass of the dichlorine, of course, this is going to be different because we have 39 millimole and the molar mass of dichlorine is 71 grams per mole. So that means 1 liter of dichlorine is going to weigh 2.8 grams. So the density is 2.8 grams per liter. Now, if you do the same calculation for dihydrogen, dihydrogen has 2 grams per mole for molecular weight. So in that case, we would have 0.2 gram per liter. So that would be a much lighter gas. This is why if you make a balloon for traveling, like Zeppelin or one of these balloons that are used, in the earlier days they use dihydrogen. And there was, in the years 30 of last century, a very big accident that the dihydrogen was exploding in the so-called Hindenburg incident. And after that they use helium, which is also very light, but is not flammable. So, but if you would use dichlorine for the balloon would go down, because it's more heavy than air. So you need to be lighter than air, and then the balloon can go up. So until now we talk about gases, but it was just one gas, one pure gas. But what about mixtures of gases? So for that we have a so-called Dalton's law, or the law of partial pressures. That means the gases, different molecules that are within the gas, they will each exert a partial pressure that is the same pressure as if the particles would be only the ones of compound A, or the particles of compound B, where you have a mixture of A and B. So, and we call that a partial pressure. So, like what we are breathing now is air. Air is dinitrogen, dioxygen. It's a gas mixture. There's about 80% is dinitrogen, about 20% is dioxygen. So, if the let's say pressure is 1 atmosphere, that means the partial pressure of dioxygen is 20% of that. It's going to be around 0.2 atmosphere. The partial pressure of dinitrogen is going to be 0.8 atmosphere. Together, they are 1 atmosphere. So we can write this equation similar in PV nRT, but now we write it for the partial pressure of compound A. It's the amount of particles of compound A, Na, amount of mole, and then RT is divided by V. It's the same volume, it's the same temperature, it's the same R for the whole gas mixture. So, and then the same for compound B. So, since this PV nRT equation is independent of the amount of particles, we can just, let's say, add up the particles Na and B, then that's the total amount of particles, and we can calculate the total pressure. So, in fact, we could say that each of the components in a gas mixture are related to the total pressure. The pressure of the partial pressure is related to the total pressure by multiplying it with the molar fraction. And I will tell you in a moment what we understand by molar fraction, but it's in fact the amount of moles of one particle divided by the total amount of moles, all of the particles. And you could write the same for P. B is then molar fraction of B by the total pressure. So if you wanted to show it in a picture, you can see it like that. So here there is a cylinder with two gases, A and B, blue and red. So you have a total pressure 4 atmosphere, for instance. And this is adding up 1 atmosphere of pressure of the red gas, gas A, and 3 atmosphere of the blue gas compound number B. So it just, the particles are in the same volume to be added, we add the pressures, and we can apply the PV nRT relation to all of the different components separately and just add them up. That's Dalton's law. So, for instance, here I thought that air is oxygen and nitrogen, but especially in Vietnam, and I think in this room, the air can also be very humid. What does it mean, humid? It means that air also contains water. So, and this water is also going to be in the gaseous form, because normally water is a liquid, but if you breathe it out, like we have been all doing here, the water gets into the air and it doesn't condense. So there will be a partial pressure of water in our mixture of gases over here. In some cases we have to take this water into account when we do our calculation. So how much water is in the air depends actually on the vapor pressure of water at a certain temperature. Now, the vapor pressure at room temperature is not that high. It's like 0.023 atmosphere, so about 2% of the total pressure. If you're saturated with water, like I assume it's going to be here, it's about 2% of the gas that we are breathing is not oxygen or nitrogen, but water. So we have to take that into account in our calculation. And this is an example where that is the case. So we have a reaction of hydrogen peroxide, and we add an oxidant, potassium permanganate, we add it in acids. Now the mixture is purple as long as there is potassium permanganate. There is a gas escaping, so the hydrogen peroxide is being oxidized. At the moment when the reaction turns purple, that means there is potassium permanganate in excess, and at that point the reaction stops because all of the hydrogen peroxide has reacted. So we know it's at room temperature, 20 degrees, and that the ambient pressure is 1 atmosphere. So the volume of gas that is escaping is 36 milliliters. And so we have all of the data now, V, B, T, and so on. What is given now also here is that the vapor pressure of water at 20 degrees is 0.023 atmosphere. So that tells you that there's going to be in that gas not only oxygen, because that's what is going to be formed, but also a little bit of water. So now we want to know how much of the hydrogen peroxide that we originally started from in our solution. So the first thing is, again, building the reaction equation with all of the right coefficients. This is the equation telling you that you need 5 hydrogen peroxides for 2 permanganate molecules, and this then gives you 5 oxygen. So this 5 and 5 tells you that for every hydrogen peroxide, for every mole of hydrogen peroxide is 1 mole of dioxygen being formed. The relation of permanganate to hydrogen peroxide is 5 to 2. Now we knew that we have 36 milliliters of gas that we obtained. So we can do a calculation. N amount of molecules, PV divided by RT. So the pressure was 1 atmosphere, but now you can see in the reds that we are doing a correction. Because the 1 atmosphere is not only oxygen, there's a partial pressure of water. And this water doesn't come from your reaction. So this is something that is just a solvent that was evaporated. So after we calculate this, we now have the correct partial pressure of dioxygen. So we divide by 0.082, 293 degrees Celsius, and there was 36 milliliter of gas in total. And this tells you that the amount of dioxygen is 1.5 10 to the minus 3 mole, or in other words 1.5 millimole of dioxygen is being formed. So, and we know that the amount of dioxygen in hydrogen peroxide is equimolar. So now we have already our solution. That means it's indeed also 1.5 millimole of hydrogen peroxide that was needed in the beginning of the solution. In fact, we don't have to know anything about the manganese of the permanganate and so on. The only thing that is important, 5 hydrogen peroxide is 5 dioxygen. Okay, so here I have 2 small assignments, and I will give the answers tomorrow. You can have a look at it. This is a reaction again in the presence of water, so you can actually apply the same thing like we did just in the previous slides, make the same kind of calculation. But I will treat it in detail tomorrow. If you want, you can have a look. And this is the second assignment, also simple one, simple stoichiometric calculation. So about how much mercury is in cinnabar. So cinnabar is mercury sulfide. Normally you can prepare mercury by removing the sulfur by treating dioxygen. So if you start from 100 grams of cinnabar, how much mercury can we form, assuming that we have a complete reaction? Okay, so I think it's time to take a break. So 5 to 10 minutes break, and then we continue with the part on solutions. If you have any questions, you can always come in front.
Ông này làm cho bên 500 à? Làm cho bên 500 à? Về chuyên mảng E4 hay là gì à? Về bên đặc kỹ thuật của E4 luôn. Lấy ra là về lịch Corona rồi. Lên là sổ. Này xã hội à? Game bị hay đấy, top game ở này đấy.
Tao nhá, tao chơi game đấy, tao chỉ yếu tập bản nhân vật.
Nó chơi sát thủ. Cứ bảo EQ
Tao thì bản nhân vật, tao là chỉ là nhân vật.
rồi đi còn em.
Ngay nhớ thì
Ra hai con thì nếu thật.
Không, nói chung là tao sẽ làm một quả để mày thôi được khoảng 300 thằng.
Hay à.
300 thằng đấy mày phải mua cho tao.
Nó thì thôi.
120 thôi, tôi hết. Mày kéo đi tao.
Thôi ra không xong rồi bé.
Tao tôi làm đúng mật nhưng mà lỡ một cái là
Được rồi, kiểu như là phải là video không. Khỏe. Nhá. Đấy, ông ấy cái kiểu chung là không thích.
của 2 tỷ 7, à 2 tỷ 7. Tao đi lại quen cái luôn.
Mình đéo học chỗ này luôn.
bạn bè của mình trong này ở trong này.
Okay, let's start again with the second part of this morning session. By the way, the slides will be provided. I'm going to send them to your teaching assistant, and she's going to distribute it to you. Maybe some of you have slides from last year. You will see there are not that many differences, but for instance, this part now is new. I introduce it because I know that you have related tutorials about this part, so to introduce the theory on solutions. So let's also do that. So let's very briefly define what we mean by a solution. So a solution is always homogeneous, and it consists of more than one component. So that means it's a mixture of pure compounds. There might be two, but there may also be more. Sometimes you have very complex solutions. I want to make also a point of compounds versus components. Many people use the two words in place of each other. So a compound is a molecule consisting of several atoms, whereas a component is a compound that is a part of a mixture. So you should be careful to use the right name for the right attribution. Now, in this course, what we will mainly see is liquid solutions, and the liquid is very often water, but there may also be organic solutions. So that means a certain compound dissolves in one of the components of a mixture which is in large excess. That is the solvent. And then a smaller amount is dissolving, that is the solute. Now, this component may be a gas that is dissolving, or it may be a solid, or it may be even another liquid. But once it is in solution, everything, of course, is in the liquid state. Its gaseous solutions also exist. Again, air, you could say it's a solution. The solvent you could consider to be dinitrogen, because it is to the major part, it is what we have, and then you could say it's a solution of dioxygen, the solute, into dinitrogen. And in fact, we know already there are some small parts of gases also that are there, like water, also CO2 is there, and argon. Argon, renewable gas, about 1% of the air that we breathe is argon. Now, again, if you want to do stoichiometry, we have to know about concentrations, about the so-called strength of solution. And this is about the contents. And so how much of each of the components in every mixture is there, how much solute is there in the solvent. So normally this is done by units, and the units we can use are, for instance, mass or volume. And this is the strength, or in some cases it's also called concentration. Now, here we have different ways of expressing strength. So, sometimes it is expressed by mass percentage. And mass percentage is weight by weight. So that means if we have 100 grams of solution, a certain part in gram is going to be a solute. So for instance, suppose we have 100 grams of solution of sodium chloride in water, and we evaporate all the water, we get 1 gram that is staying behind. Then it's a 1% solution of sodium chloride in water. Another way of expressing is volume percent. This is used, for instance, to express how much alcohol there is in a certain drink. So if you look to a beer can, you will see it's 5%, or maybe 4.8 or 5.3, 5%. So that means if you have 100 milliliters of beer, that's going to be 5 milliliters of pure alcohol. If it's a Belgian beer, it's 10%. Belgian beer is very strong. Okay, mass by volume. Same thing, but now we consider not 100 grams, but 100 milliliters of solution. And you know that if it's water, it's more or less the same, yes? Because 1 liter of water is weighing 1 kilogram. It's only when you have very heavy solutions, very strong solutions, that the density might be different. But for dilution, the mass by volume percent or mass percent is going to be more or less the same in water. Now, if you want to express very, very low concentrations, maybe of a very toxic substance or toxic gas, then we use ppm or ppb. So, and it means by million or by billion. So 10 to the 6th or 10 to the 9th unit. So this can be weight, volume, or weight, volume, but it's these numbers are going to be actually quite low. For instance, they would say that a certain toxic gas, like chlorine, we cannot have more than, I don't know, 10 ppm in the air, otherwise it's too dangerous, for instance. Or in the soil, there's a certain contaminant, we don't want it to be more than so much ppb, parts per million. Then, the more chemical ways of expressing concentrations are per mole. And this is what is useful for stoichiometric calculations. So the mole fraction, we have already seen what it is for the partial gases. So that means now we calculate mole per mole. So we have the total amount of moles of the mixture, including the solvent. And then we take the amount of mole of one particular solute. So this number is always going to be less than 1. Yes. A number of 1 means it's the pure solvent. So normally this is going to be a small number, much smaller than 1. This is used, mole fraction, mainly for calculations with gases, not with liquid solutions. For liquid solutions, the most common way to express is molarity, expressed by capital M. So that's the amount of mole per liter, and we already, in a couple of the previous slides, we have used this, of course. A variance is the molality with an L and not an R. Molality is actually 1 kilogram of solution and not 1 liter of solution. Again, for diluted solutions in water, it's going to be more or less the same. But what is the advantage of using molality? It is actually independent of the temperature, because the weight stays the same when you have different temperature. But the density doesn't stay the same. The water expands when you heat it. So that means density is changing, and then you have a different molality, because you have more volume for the same amount of moles. So if you want to do calculations at different temperatures, molality, small m, might be useful. Although we will use mainly molarity with an R, big letter M. In titrations, sometimes also normality is used. Now, this is the amount of equivalence, not the amount of mole per 1 liter solution. Now, what is the difference between mole and equivalence? Well, you have, for instance, an acid, like sulfuric acid. Sulfuric acid has 2 protons, H2SO4. So that means 2 equivalents of protons. And so if you do acid-base titration, and we have 5 molar of sulfuric acid, that's actually 10 normal, because 2 protons. So it's good to keep that also into account. Now, in the most what is following, we will use molarity. So that is, I think, the most important to remember. This is maybe too simple for you, and I guess you know this all from previous studies, but just to keep in account, if you're doing any stoichiometric calculations. What happens if we dilute, mix, or distribute? And what happens with the amount of moles? What happens with the concentration? These are 2 different things. Sometimes I use again the example of alcohol. People drink alcohol because it has an effect on their body. How much effect depends on the mole of alcohol, the amount of mole of alcohol that you're drinking. So let's see, of course in chemical lab it's different, but let's see the analogy here. Now, if you dilute, you just add solvent. The amount of mole is not adding. So if you take a glass of vodka and you add fruit juice, the same. If you drink it with fruit juice or without, it will have the same effect on your body, because the mole of alcohol has not changed. Mixing it would then be with another solvent, the same thing, it doesn't change. But now, the effect of distributing, that means we have the bottle of alcohol, the same amount of mole, but if I drink all of it alone, it's going to be a totally different effect than if I distribute it over the whole auditorium and give every one of you 1 milliliter. You will have no effect. This can be expressed quantitatively because the partial volume is divided by the total volume, and for instance if I divide it over 100 people, the effect will be only 1/100 of the effect what I would have if only one person would drink. Now, the second column is what about the concentration, because this may be important in some calculation. So, if you dilute, the molarity is going down. It's going down by a factor that is the factor that is the volume before divided by the volume after. That means, again, using the example of the alcohol, if we take the vodka and we taste it, it's going to have very strong taste. If we dilute it, then the taste may be easier to drink. This is the molality, the concentration. We feel the concentration in our mouth. So we can make it more drinkable by diluting or by mixing. In both cases, the effect is going to be less by the factor of volume before divided by volume after. Now, if we distribute it, again, if I distribute this bottle of vodka over the whole auditorium, everybody is going to have the same taste. Because it's a homogeneous solution, and you all will have the same effects, at least the same taste in your mouth. So that's going to be the difference here. Okay, so we come to the so-called colligative properties. And so the gas law, ideal gas law, was already one expression of colligative properties of particles in the gaseous phase, meaning that the equations are not dependent on the type of particles, but only on the amount of particles. So now we will talk about colligative properties in solution and not in the gas phase. So again, these properties depend on the solute particles, so not the solvent, but the solute, and we assume that the solute particles are non-volatile. So they remain into the solution. Maybe the solution itself, the solvent, could be volatile like water, but not the compound that is the solvent. We will treat 4 different colligative properties, including vapor pressure lowering, boiling point depression, boiling point elevation, freezing point depression, and osmotic pressure changes that might occur. Solutes, the compounds that are dissolved into a solution, might have 2 different characters. They might be ionic, so in most cases these are salts that consist of cations and anions, but also acids like HCl, splits in protons, H+, Cl-. These are ionic solutes. That means they produce more particles, because the HCl is not just one molecule, but it's 2 different particles, protons and chlorine minus. So the covalent solutes, those do not split into ions, so that means 1 mole of solute means 1 mole of particles. So it's important to keep in mind, because the amount of particles is actually determining how much of this colligative property we are actually having. So the first one of these properties is the relative lowering of vapor pressure. So a solution is a liquid, and any liquids may go into the gaseous phase by contact with the environment. For instance, water is slowly evaporating. There's a certain vapor pressure of the water, and it is seen that if you add some substance to water and it dissolves, the vapor pressure is going to go down. And this has to do with the so-called Raoult's law for non-volatile solutions. So that means if you add non-volatile solutes, for instance a salt or sugar, volatile, to solvent, you form a solution that now, because there are some molecules in between the solvent, there is less contact with the outside world, and the vapor pressure is diminishing. So, and in fact you could say again, with the molar fraction, the partial pressure of the solvents, molecules, is going to be directly proportional to the molecular fraction. And that means if you have pure solvents, no solutes, the molar fraction is 1. It's 100% of the solvent. Then the pressure is the vapor pressure, as we expect. But as soon as you start adding new compounds and they dissolve into the solvent, then this molar fraction is going to go down, and the pressure, the vapor pressure, is going to go down along with it. So, and you could say indeed that this is going to be, the difference in pressure is going to be the original pressure when we have pure solvents multiplied by a factor 1 minus x1. x1 being the molar fraction of the solvent. Now, if the molar fraction of the solvent is 1, in other words, it's pure solvent, then it's 1 minus 1, so this is 0. In that case, we don't have, of course, any change of pressure. So, but for instance, you have 99% of solvent and 1% of solute particles. So this 1 minus x1 is 1 minus 0.99. So that's 0.01. So it's going to be about 1% lowering of the pressure. So you can see in this case, if you have very strong solutions, maybe sodium chloride 30% solution, you can have a relatively strong depression of the vapor pressure in such a case. Now, just showing you a picture that shows you the idea behind the lowering of this vapor pressure. So what is actually happening, so where the solvents or the liquid comes into contact with the air, particles might go up into the gas according to the amount of the vapor pressure. So, and this is occurring because there is a contact surface between the gas phase and the liquid phase. Here we have the same surface, but you see the particles at the surface are not all of them solvent molecules. Some of them are the red particles, and they are not volatile. So they take the place of a solvent molecule, so this can no longer go up into the air. And that's the idea of why you actually have a lower vapor pressure. Now, closely associated with the vapor pressure is the boiling point. Because in fact, if the pressure, the vapor pressure, is the same as the pressure of the ambient, like in this case now 1 atmosphere, and so if you have a vapor pressure of 1 atmosphere, the liquid starts boiling. For instance, for water, at 100 degrees Celsius, the vapor pressure rises up to 1 atmosphere. And then the water starts boiling. If we raise even above that, we get a much higher vapor pressure. And then things could boil up very fast. So then it means the vapor pressure and boiling point are in fact related to each other. Now, we can measure. Normally, if you have pure water, we put a thermometer in it, and we look at the thermometer when it starts boiling, it will read 100 degrees Celsius. If you have a salt solution, or a solution of a non-volatile compound, you will see that this temperature is higher. There will be a difference in boiling temperature, delta TB, is the difference in boiling temperature. And there's a formula for it. We can say that this is made by two factors. One factor is the concentration, and normally the concentration is expressed in molality, because we need different temperatures. It's better than molality. And this is then multiplied by the so-called ebullioscopic coefficient. This coefficient is different for every different compound. For instance, for water it's about 0.5. For larger molecules it's larger. So you can find these ebullioscopic coefficients in some tables. So there is a variant which is a little bit more correct and which includes the so-called Van 't Hoff factor. Van 't Hoff was a Dutch scientist of the 19th century, and 19th and 20th. So this factor takes into account how much particles you get, because if you dissolve 1 mole of substance, as I explained, it doesn't always give 1 mole of particles. Sometimes it gives 2 moles or 3 moles. So for glucose is a sugar, it's a neutral compound. The molecules of glucose, when dissolved, stay glucose. So that means the Van 't Hoff factor is 1. Sodium chloride, if it dissolves, it gives 2 particles, sodium plus and chloride minus. So if you have a complete dissolution, normally you can assume that the I is 2. Sodium sulfate, you get 2 sodiums and 1 sulfate. That's 3 particles. So here the Van 't Hoff factor will be 3. Again, we assume that salts that are dissolved are completely splitting into ions, which is an approximation. It's not completely true, but let's say for the sake of calculation, we assume it to be like that. That means we can actually do calculations with this. The KBs of the most common solvents are known. So that means now we can either calculate how much is going to be the difference in boiling point, or if you measure the boiling point, we can measure the molality. And from that we can also get some additional data. So for instance, we could calculate the molecular weights of a certain unknown substance by looking at, okay, we dissolve so much gram of this compound in this solution and we see the effect on the boiling point. And then from that we can see, okay, what is the concentration? If we have the concentration and we know the amount of gram, we can calculate it back to the molecular weight. And this is called ebullimetry, and it was used until about 100 years ago to calculate molecular weight. Now we have much better ways, a spectroscopic way and so on, to calculate molecular weights, but this used to be one method to do it. So if it's a mixture of compounds, in fact you only get the amount of particles, so that means it's a number average molecular weight. For instance, sometimes it's used for polymers, and then the polymers contain different molecules of different molecular weights. You get the number average molecular weight. We should say that this is not really a very accurate way of measuring molecular weights. You get an approximation, The boiling point is not so easy to measure exactly, and also there might be non-ideal behavior, especially at high concentration. And in the non-ideal behavior, the formula is not exactly correct. A third way of expressing colligative properties is the freezing point depression. So it's the opposite. Actually, the freezing point goes down rather than up. And so normally, for instance, for ice is solid water, and we know that ice is forming at 0 degrees Celsius. And so that means if you take liquid water, you bring down the temperature, at a certain point everything starts to freeze. Now there will be a depression in temperature. You will have to go, if you add salt to the water, maybe you have to go to -5 or even lower before you can actually start freezing. And also you can measure that by putting a thermometer in your solution and seeing how much is the difference in freezing temperature, delta TF. And again, you see it's a similar formula. I, the Van Gogh factor, multiplied by M, the molality, and Kf, in this case, cryoscopic coefficient. Not ebullioscopic, but cryoscopic, because it's freezing. So these coefficients are in general larger than the ones based on boiling, so it's more precise because of that reason. So cryoscopy was used a lot more previously for determination of the molecular weights. It's more precise because it's bigger, but also it's easier to see the crystallizing points, freezing points. It's easier to see it than for boiling. Now, why does this lowering of the freezing temperature happen? It's actually due to the fact that the solid molecules are hindering the crystallization. They get inside of the crystal lattice and they stop due to entropy. I will explain entropy later. They stop the crystallization. Now this has some application in real life. For instance, I think in Vietnam you don't have this problem, but in the north of Europe we have every year there's snow, and this blocks the roads. Very difficult to drive. Well, people are then distributing salt onto the road. And what does the salt do? It mixes with the solid water and forms a solution which cannot freeze so fast anymore. So if you have a temperature of -5 outside, the salts will actually bring down the freezing temperature so that we don't have any more ice or snow onto the road. This is the way that people used to make ice cream. Ice cream already exists from medieval time, and you can ask yourself how it's possible to make it if you have no electricity. Because normally you use an ice machine with electricity to make the ice. People used to make ice cream from putting granulated ice and adding salt to it. And then you get some solution that can go down to -10, sometimes -15 degrees Celsius. If you put your milk mixture and you stir, after some time you're going to have ice cream. And so even the Arab people already knew that when they made sherbets from fruit juice and milk. Also, the ice cream, to have interesting taste in the mouth, It also contains sugar, fat, protein, and so on. These particles also make sure that you don't have crystals. So crystals in ice not so interesting to eat, and this is more like what they call a sludge. And then you have the perfect ice cream. Also in northern countries, some plants have a strategy to survive, because if your cells are frozen, they might die. So they add proteins or sugars to the juices inside of the cells. And because of that, these plants can stand to -10 degrees or lower, and still they remain green color. Then the last part on qualitative properties is the osmotic pressure. Now, again, if we have two different solutions, and one is in fact not a solution but a pure solvent, and the other one is the solution containing solutes, and you make some contacts between these two solutions with a membrane. Now, a membrane could be some polymer, or it could be some organic molecules. What this membrane does is it is let's say permeable, and by that we mean molecules can move from one side to the other, but not all molecules. Small molecules, like the solvent, can move, but the solid molecule, they cannot move, they stay behind. So in that case, in fact, the solvent is going to move and wants to dilute the solution that contains already solute. And that means now there's going to move some solvent into the dissolved compound, and one part will have more volume than the other. So let me show how this will be. So here we have our semi-permeable membrane. This is pure solvent. This solvent contains other molecules. So if the solvent can move, but not the particles, the solvent wants to move in to dilute. And that means more solvent goes in, and you can see there's actually a difference in volume. Now, if you want to restore the original situation, you would have to put pressure on the right end. And then you push back the solvent through the membrane. And this pressure, this external pressure, is in fact the osmotic pressure. That's what you need to restore the original situation. It can be calculated from the density, the volume of the displaced solvent, and so on, to know the force that you need for the osmotic pressure. Again, this is a completely colligative property, not dependent on the type of particles, but only on the amount of particles. So you can see the pressure pi. Again, we use I for the Van 't Hoff factor, the amount of particles. C is the concentration, and then RT is like in the gas law. You can see this looks very similar. This is like PV and RT. Almost looks the same. So with R the ideal gas constant and T the absolute temperature. So why is this osmotic pressure important? So for instance in biological cells, So cells regulates osmotic pressure by having solutes. So we can call environment hypotonic, isotonic, or hypotonic, depending on the fact that you have the same osmotic pressure, then it's isotonic. Yeah? So a lower one, hypotonic, or a higher one, hypotonic. So here we have red blood cells. In hypertonic environments, actually that means what is surrounding the water contains more particles. So the solvent, water, goes out of the cells and the cells shrink. In the hypotonic, it's the inverse. So the water that is surrounding doesn't contain so many particles. The water goes in to the cells and they are bloating. Then we have the hypotonic. So, for instance, plants contain cells, and a plant, of course, can stand up. It can stand up because the cells are bloated, so they use this osmotic pressure to be able to stand up. An important application in countries where there is very little water, not like Vietnam, but for instance Arabian countries, they have deserts, but they are next to the sea. They can take back the water from the seawater by reverse osmosis. So what do we do? It's in fact, it's similar to this one. You push the water back. So here we have seawater, contains sodium chloride and other salts. Here we have the membrane, and we apply the pressure. We push through the water, but all the compounds that we don't want, the salts, we are staying behind. So, and then afterwards you get more concentrated salt solution. We can put it back into the sea, and you get water which almost contains no salt. This is water that we can drink, or they can use for agriculture and so on. So this is a convenient way, but of course you need power. But they have a lot of energy. That's not the problem. You need energy to push through the water and through this membrane. Okay, I think with that I'm at the end of this. So we will have another break. So and then I continue for the beginning of thermodynamics chapter. I think we still have time for half an hour. I think. Okay. Any questions you can ask? I'm here in front. It's actually, you can consider it like a mixing. because dilution will be you add water. Mixing is mean you add the active solution or something else.
Đâu đây thằng kia làm chân nó mở nào. Correct là Chelsea.
And normally you don't get higher pressure.
Chelsea là thành công. Bé chỉ ai khi với cả Vera và David Villa thôi. Chứ còn anh Lampard một bước.
Zera nó có đá ngoài đá Liverpool hay đá đội nào đâu?
LA Galaxy và tuyển Anh.
LA Galaxy là nghỉ hưu với đá đúng không?
Treo giày phải sang Mỹ đá. Thì sự nghiệp đỉnh cao nó ở châu Âu và trước thì anh tính sự nghiệp đỉnh cao nó ở châu Mỹ ở Nếu anh tính đỉnh cao nó là một viên đợt vừa rồi là Aston Villa, bây giờ thì cắt kèo rồi. Chứ nhìn như anh bạn Frank Lampard này thì phải 12 năm
Anh bắt được trước
Chelsea trong buổi sang Everton với mình ông là Xabi Alonso cái chỉ số người trẻ đấm nhau cũng được chuyển sang cái phần Samoya và này chuyển sang đá nhạc trường
trước rồi có cái thằng nào thì tóc dài dài nhỉ? Dài dài một tóc vàng vàng. Red.
Đội nào?
Liverpool.
Red đây. Theo cả bờ đúng không? Ông Wood, Fernando Torres. Cắt là sẵn trẻ rất cuối ở Liverpool
có 4 này. Nếu mà chúng tôi không làm
thế xem bảo khi làm học của tạo mặt hết rồi.
nhưng mà tìm lại cái phải
chưa mấy trận đấu nhỏ là nhiều đá nhiều nói chung là áo số 9 của Chelsea là bây giờ đến Drogba lúc đầu sáng
chí sau bắt được
ngày trước Chelsea số 9 của Alvaro Morata Phong Lan này Áo ra khỏi cái hội đồng anh sau 8 năm đâu. Tao đang cọc vậy. Trên ngồi nói chung là chịu khó lên đi. BK đã căng rồi.
Được cặp anh đây nào. Ơi, bạn ngồi cái này xuống. Mẹ là bên nét.
Mày lên đây ngồi.
Này đỡ cho vào. Buồn thế.
Anh thì con mẹ. Nhỏ mình chưa đâu đấy. mày không lên chốt con tao mà chơi.
Thì đâu nhỉ?
Tao mày thích mà.
Okay, so let's start our third session. I think maybe it won't be that long. Several students already asked me what about the handbook? Is it the same as last year? I think yes, you could use the same book as last year. I think it's one by Ebbing and so on. But in fact, any textbook, English textbook on general chemistry contain the same. So whatever textbook you find is going to be okay. But the one of last year is perfect and contains everything. But in fact, what I tell you here in these slides is of course the most important. I think if you know that part, it's already not bad. And if you want to get more information, of course, you can read in the textbook. And also you can ask the assistant, the teaching assistant during the tutorials. They can also direct you to more information. But normally I would say if you understand the things that I have been talking about, this should be sufficient to let you pass the course with good result. So that should be. But actually I'm not in any way referring to the handbook during my teaching. But it's just for you, maybe of some interest for additional reading. Good. Let's go to the next chapter, which many people consider to be relatively difficult, because it introduces some new concepts. And that's a chapter about thermodynamics. And of course, thermodynamics can be applied to any physical or chemistry process, but we are mainly interested here in chemistry in this course. So, and thermodynamics have to do with energy. And as a result of a chemical process, there may be some exchanges of energy. And we can consider two parts. One part being the system, and the other part being the environment. Normally a system is within an environment, and it's a theoretical concept. What could it be in practice? So a chemical system could be a flask, where you're doing a reaction, or a reactor. So the environment, that's everything around it. Maybe there's a water bath where you're taking the heat of the reaction, or maybe putting heat inside of the reaction. So the heat is going to go from the system to the environment, or from the environment to the system. These two are of course two different situations which we have to take into account when we discuss the thermodynamics of a reaction. Now, we can consider different types of systems. A system could be open. That means there's a free exchange. Matter could exchange, energy could exchange between the system and the environment. That's typically something in a chemical lab you don't want. You want to contain your chemicals into a flask. You don't want the system to be open, you want it to be closed. In a closed system, there is no matter exchange. That means you're boiling your reaction, everything stays outside, you can't smell your chemicals. But what is possible is that there is an exchange of energy. In an isolated system, both the energy is staying inside and the matter is staying inside. In general, the chemical practice are closed systems. And so we keep the matter inside, but there may be energy exchanges between system and environment. Let's discuss energy. There might be several types of energy. In the context of chemistry, we can talk about work energy, which is a structured form of energy, and we can talk about heat. Heat has to do with an increase in temperature of your system or environment. So it might be that you exchange, and for instance, the system is delivering work onto the environment. For instance, a gas is expanding. So if the system delivers work, that means the system loses energy. That means the sign of this energy is minus. So it's a negative energy because you're losing it. It could also be that the inverse is happening. So you have a reaction flask and the environment put pressure on it. Now the system has gained energy because the work is coming from the environment and going to the system. So same type of work, but the sign is actually changing. Now it's a positive sign instead of a negative sign. In the thermodynamics, very important to know the direction of the arrow. So to know that it is going from the system to the environment or from the environment to the system. By the way, work, typically it would be like some kind of force that you exert over a certain distance. That's something you know from physics. The two types of energy are very different. Work is, for instance, has to do with expansion of a gas, whereas heat is just has to do with the temperature of the molecules. If you have an increase of temperature, it means your molecule is starting to vibrate and behave in general more chaotically. If you cool down, it's the inverse. The movement gets slower and slower, and your molecules are less chaotic. So there are some reactions that involve heat. For instance, if you would take a bottle of sulfuric acid and you add it to a concentrated solution of sodium hydroxide, you would see that the temperature increases a lot, even it might start boiling, that you have so much energy that you are remaining. But on the other hand, as long as it doesn't boil, there will be no expansion, no gases escaping, and so it's only the heat as a result of the reaction. But it could also be that the gas is escaping. And this escape is a physical process. There's a pressure, there's a force that is exerted by the system where the reaction is happening to the environment. So for instance, suppose we have calcium carbonate, salts, and we start heating it at a certain point. It will release CO2, which is a gas. It will form calcium oxide, which is non-volatile. And so this is normally expressed by putting between brackets S for solid and G for gas. Now, suppose you do this in a reaction vessel, of which one of the sides can move. If it's completely closed, it means the gas cannot escape. You just increase the pressure as you will increase the amount of CO2 gas. But now we have one part that can move. That means we move that part, and that's work that is actually being done by the system. And that's the so-called expansion work. And this actually is the pressure by the volume that you're actually displacing. So we actually can just simply calculate this energy by multiplying the expansion pressure by the volume. Interestingly, there's a minus sign. Why is this minus sign? It's because the system is giving away to the environment expansion work, so it has lost energy. So this is a negative number. So maybe it will become more clear if you look to this figure. So this is like a gas volume. So if we actually are heating it up, the gas expands, and then this piston, one part of the reaction vessel which can move, is going to move up. So we put in heat and we release work. The opposite is also possible. The system is actually going to put in energy by applying pressure onto a gas mixture. It will gain energy, but it will lose the energy by giving it to the environment and cooling down. So it means the work and the temperature or the heat are in balance. And this very often we see that there's compensation of the two types of energies. So heat is normally abbreviated by Q. I think it comes from the Latin calor. And we can measure heat. And we can measure, for instance, that an environment, like a heating mantle, is taking up some heat from a system by an increase in temperature. And so the heat is the amount of the water, for instance, that we have in the heating mantle, expressed in moles. The heat capacity, which is a property which is related to the water or to any compound that we are using for the bath. And then what we measure is the difference in temperature. And typically we do that in a calorimeter. That means it's a mantle around our reaction which takes up the heat, and we have a thermometer where we can very accurately see what are the differences in temperature. And so heat capacity of water is known, it's 75.3 joule per Kelvin per mole. So that's known. We know also how much water is in our bath, so we can know N. And so that means we can directly calculate the heat that is coming out of a reaction. So, and this is quite important. It gives us an experimental way to know how much heat is evolving from a reaction system. Because by the temperature difference, we can measure it. Again, of course, we have to take into account which direction is this going. If the reaction is exothermic, it means there will be energy going out, heat goes out of the system into the environment. So if the reaction is endothermic, it will be the opposite. So in fact, the heating mantle or the water in the heating mantle will go down in temperature in that case, because the environment is losing energy to the system. And this brings us to internal energies of systems. So each system has a certain energy which is the sum of all of the possible energies that you are having. And this is normally expressed by U. And what we are mainly interested in is not the internal energy itself, but the differences in internal energy that we have as an effect of the chemical changes. So, and these may be, let's say, two factors. Either we have heat that is evolved or taken up, that's Q, or we have the work that is being exerted by the system to the environment, or by the environment to the system. So we have these two, and you see that these are indeed two different expressions of energy. You can just add them up to each other, and you get the internal energy. And this brings us already to a first law of thermodynamics. And this first law says that in an isolated system, there's actually the internal energy has to remain the same. Or in other words, the difference in internal energy has to be zero. Or you could also say energy is conserved. You cannot destroy energy, it remains the same. So, isolated system, you could consider it to be together the system and the environment. Together they are an isolated system. So that means the sum of these two exchanges, of these two internal energies, has to be zero, according to this first law of thermodynamics. It's like what we know in physics by action and reaction. If the system is gaining energy, the environment has to actually have the same amount, but then negatively, to compensate and bring the total energy change to zero. Now, if we have processes which do not involve gases, even if we have a gas and we keep the volume constant, then we don't have any expansion energy. So, volume constant means it's a closed cylinder, it cannot expand. So no expansion energy. And then it means all of the exchanges between the system and the environment are heat exchanges. And they could be in one direction or they could be in the other direction, depending on the case. And this is, of course, delta V is zero because it's constant. So the expansion energy automatically becomes zero. So in such a case, it's very easy to measure thermodynamics because you just use your calorimeter, you measure your difference in temperature, and you know this QV, and you can measure it for any reaction. This is first in law of thermodynamics. This brings us to a first of thermodynamic functions, and that's the so-called enthalpy. Enthalpy is given the capital H. Again, we are mainly interested in differences in enthalpy, delta H, as a result of a certain reaction. Now, enthalpy is actually can be made by the internal energy and by adding the term PV to its. And again, we can express it in the delta function. So delta H is delta U plus P delta V. So now if you have a system at constant pressure, not volume, but pressure, that means it's like a system where the volume can expand, like you have seen earlier. So now that means the delta H is given by U, and U is Q minus P expansion delta V. So this is when the volume expands, there's a certain work being done. But you see, the term P delta V is exactly the same. So that means now the enthalpy only refers to the heat at constant pressure. So again, that means when we are at constant pressure, we can determine in a calorimeter this delta H without problem. By the way, the term enthalpy comes from the Greek talpein, heat. So there's a direct relation between heat and enthalpy. So in reaction with gases, we can look at the formula, and we know from previous chapter, PV is nRT. So we can replace it in the equation for the enthalpy. So that means we can at that moment calculate our enthalpy. So you could say that delta H and delta U are more or less the same, as long as we don't have any gases. Because this only refers to work based on expansion, and if you have no expansion, normally solids and liquids do not expand too much. So you could say delta U is going to be more or less delta H. It's only in the time where you have some kind of difference in the term delta N gas by RT that it will be different. Now, even it could be that you have gases in your reaction, but there is as much gas before and after the reaction. In that case, delta N is 0. And also in that case, delta U is equals delta H. So, but in the reaction that we saw previously, calcium carbonate gives calcium oxide and CO2. Delta N is 1. Because we generate 1 mole of gas and we didn't have gas before. In that case, we will have a difference between the internal energy and enthalpy. Now we can define the standard enthalpy. This is also delta H, but there's some kind of small zero. This is the enthalpy that are in a certain standard conditions. And what is the standard condition or the standard states? It's the pressure is always the same. It's 1 atmosphere. So any lower or higher is not standard. Solid or liquids could be the most stable states. In that case, of course, no pressure. So if it's a dissolved substance, we are having 1 molar concentration. Anything higher or lower, again, is not a standard state. Not part of standard conditions is the temperature. So we can still make changes in our temperature. Although in many cases in tables we take room temperature. Room temperature is set to be 25 degrees Celsius or 298 Kelvin. By the way, the influence of temperature on delta H is in fact negligible. So we can consider, if you see the delta H in the table, we can use it at any temperature, it remains the same. There's no influence of the temperature. Now, we will discuss a few different processes and what is then the effects on the enthalpy. For instance, we discussed melting and freezing in the previous chapter. So we need energy to melt the solids, or energy will be released if let's say we take water and we convert it into ice. So then this has to do with a certain melting enthalpy, delta H melting, you could say. This is of course of a solid, and that's the energy that is needed to convert the solids to the liquid phase. So if you go to that direction, it means we need to add energy to bring it to the liquid phase. This means you will have a plus sign, because you need to add energy to the system. If you have the opposite, so you start from the liquid and you go to the ice, it will be a negative sign, because we invert the direction of this physical process. So this is a relatively low amount of energy, 6 kilojoule, and it's expressed per mole. So for it's water, so 18 gram of water, we need 6 kilojoule to convert it into ice. If we melt 18 gram of ice, we are going to release this 6 kilojoule per mole. This will be minus. The next process is vaporization, boiling, converting the liquids to the gaseous phase. So delta H vaporization. If you take the same molecule, water, we know at 100 degrees Celsius it's going to be boiling off, and to do that you need almost 41 kilojoule per mole. This number is bigger than the 6 kilojoule per mole. Why is that? Well, if we convert the liquids to the gas, almost all of the interactions between the molecules are cancelled, because the gas behaves like ideal gas without interaction between the particles. In the liquid phase, we have hydrogen bonding between the water molecules. All of these hydrogen bonds have to be broken. That costs energy. If we have the same from two condensed phases, solids, liquids, we break some of the interactions, but not all of the interactions. So for that, we need only 6 kilojoules per mole. To break all of the interactions, we need 41 kilojoules per mole. But these are not bonds, but there are interactions, hydrogen bonds between the molecules. Again, positive, because you know if you want to boil water, you have to heat. It won't go by itself. So we need, the system gains energy, the environment has to put heat into the system. Then it's also possible to go directly from the solid state to the gaseous state. And of course in that case, this is more or less, but not exactly, electrons together, then this is at 0 degrees. So that means ice could in principle directly go to water vapor. That's the process what is happening here. It's not exactly the sum of the two, because one is at 0 degrees and the other one at 100 degrees. It's not exactly the same. Now, the previous examples, melting, subliming, and boiling are all physical processes. What about chemical processes? So here we have ionization, meaning we remove electrons from atoms. For instance, in this case, the magnesium atom, it can remove one electron and then a second electron in 2 steps. We go to magnesium plus and magnesium 2 plus. So you can see the energies to do that are much higher than the energies that are needed to break physical bonds. And so we are in the hundreds of kilojoule. The second step is, of course, more difficult because you have to remove an electron from something which is already positively charged. So, by the way, you can find such energies in the tables, and these tables also I will give to the teaching assistant and they can be distributed later, because we might use such tables for exercises later on. This is, by the way, for the atoms in the gas phase. Here we have the uptake of an electron by an atom. So the atom is chlorine, and you get a chloride. So it's also an enormous amount of energy. But interestingly, the sign is negative. So what does it mean? That actually the chlorine atom likes to accept an electron, and it will actually release energy because of that. So the nucleus of the chlorine is positive, the negative charge of the electron gets attracted by it, it releases energy, the system loses the energy that it has released, and therefore it's a negative thing. So this is a spontaneous process. The previous processes, boiling, freezing, you had to add heat, but in this case it is a spontaneous process. Also the electron affinities you can find in tables, you can find the values for different atoms. So this is a covalent bonds in HCl that we're actually splitting into different atoms. So you could say this is like the inverse of making the bonds. We are splitting the bonds between two atoms. Now, typically this will be a positive value. It is called the bond energy, but in fact it's the energy that is required to break the bond. Again, it depends on the direction of the reaction. If you want to break the bond, that's difficult. You need to put in energy, and then the energy is positive. If we start from hydrogen molecule, hydrogen atom and chlorine atom, and we go to HCl, that's going to release energy, then the number will be negative. And so also there, these kind of bond enthalpies you can find in tables. Sometimes it's an average bond enthalpy when you have several bonds in the same molecule, like in water. For instance, to break water, you need on average per oxygen-hydrogen bond you need 464 kilojoules per mole. The compounds in general in nature do not occur as atoms. They occur in a bound way. And so that is a spontaneous situation. To convert them to atoms, we have to add energy from the environment to the system. So this is a positive value. So for instance, carbon. Carbon is a solid, but it can be converted to carbon atoms in the gas phase. To do that, we need per carbon atom, we need 716.7 kilojoules per mole. You could also say this is a sublimation energy for carbon, because we actually convert the solid to the gaseous phase. You see sodium, the metal sodium, the bonds between the sodiums are much less strong. So it's easier to convert sodium to sodium gas. It only requires 107 kilojoules per mole. These are always endothermic processes. If there would be exothermics, it would mean the compound would spontaneously fall apart. So if a compound is stable, you have a positive enthalpy of atomization. And then the reaction enthalpy, we're going to have a lot of those also in, I think, exercises. This occurs quite a lot. This, of course, is the energy per reaction. So now it's not per mole. It belongs to the reaction equation. So you see here, we have the reaction that we have seen previously in the previous chapter. Combustion of hydrogen. And you actually are preparing 2 molecules of water from 2 molecules of hydrogen and 1 oxygen. So the standard reaction enthalpy of this reaction is minus 571.6 kilojoules. Not kilojoules per mole, because it's per reaction. If we would want to calculate the combustion energy of dihydrogen, then we would calculate it per molecule of dihydrogen. Then it's half of it, because we have, in this reaction equation, we have 2 hydrogens. So that means we would have 285.8 kilojoules per mole of dihydrogen. So it's important to look to the difference between that, between the reaction enthalpy and, for instance, combustion standard enthalpy, because it's not the same in this case. So this is enormous energy. This is the reason why dihydrogen actually burns explosively, because it releases an amount, a really very big amount of energy. So here we see a picture. It's a very old picture from 1937, and this is the incident that I already described in the previous class, the Hindenburg, which was a Zeppelin air balloon consisting of dihydrogen. I think some fire was occurring, and at that point, you know, the people were leaving. So in the Zeppelin, there were like 100 people on board, and most of them died as a result of this incident. And after that, people didn't want to use Zeppelins anymore. And as you know, much more popular, of course, is airplane. This incident was probably one of the reasons. Okay.